There's a weird thing for the test that you can write on your reference sheet. Degree mode for every section but 6.5. Make a note somewhere. We're now going to radian mode. Or we could go to radian mode. Now, if you guys notice, isn't there an example you've already written down that is in degrees?
Yeah.
Okay, so when we're doing examples today, when you're doing homework, just realize in section 6.5, it can go degrees or radians, because we're not specifically talking about vectors in physics anymore. We're actually going to be like, okay, we've done all this work with oblique triangles. What are oblique triangles again? Not right. Good. Not right angle. That was section 6162. What do we do if we have side angle side, or angle side angle, or side side side, or okay? Yeah, we can do log sines or log cosines, but those new forms, right? And then we have new area formulas too to make our life easier. But how to deal with oblique triangles, and then we're like, okay, so now we're ready to tackle real life problems, or at least the really, really basic ones. Vectors. I know it's really hard when I say really basic. It's the very foundation, like the very basics of vectors, which are a hard topic. And then we did more vectors. And then we figured out the dot product and how to use that. And we were doing all these applications that were physics-y. But then section 6.5 says, guess what? All the stuff that we were doing with vectors, the math, not like the applications, not the modeling of forces, none of that stuff, but the math, the formulas that we were using, are actually really, really helpful for a different way of writing a complex number. We've talked about the old-fashioned way of writing a complex number, a plus bi. This is like old school. I'm going to put it in green parentheses because we've been here, we've done that. We've seen that I squared is -1, etc. What we didn't do, because we weren't ready with the math, basically, is we didn't see that there was actually another way of writing a complex number that you guys should highlight right here and make sure to get on your reference page. There's not just the standard form. There's also what we call a trig form. There's not just a standard form, there's also a trig form. And right here, these thetas, maybe this is where we can take our note or put our note. These thetas can be in degrees or radians. It's the only spot in the entire chapter, the only types of problems in the entire chapter where theta can be degrees or radians. So something for you to just kind of keep track of when you're doing the review, when you're doing homework. When you have your calculator on your desk for the test, which you're allowed to have for the entire test. It's just a realization that you should be in degree mode the whole test unless you come to a complex number, and then you might need to go to radians. So let's figure out how on earth or where on earth the math formulas are super similar, okay? If the math isn't really new, but the application is new, it's not the physics anymore, now it's the complex numbers, let's figure out why. So way back here, the very beginning, to graph complex numbers, you might be like, no, complex numbers don't show up on graphs. They don't show up on real graphs. Complex zeros weren't really there, but if you notice, things have just changed. The horizontal axis can be called the real axis, and the y-axis can be called, the vertical axis can be called the imaginary, which I know is weird. So it's not the real normal number system. It's using a horizontal vertical coordinate plane to do something else. We can graph complex numbers if we're trying to look at them graphically by going over horizontally, either right or left, the a component, which in this one is a positive 3, so I'm going to go right 3. And we can go the imaginary component up or down, positive or negative, based on the b. So if you want to think about it, we're going positive 3 and, well, wait a minute, we have to go positive 3 and negative 2i. So instead of putting the dot at the negative 2i, I'm going to label the negative 2i and say, well, I need both. I need the real and the imaginary. Kind of like the x and the y. And you usually draw a line from the center. It could just be a point. But see, it's like a vector in that there's a horizontal component and a vertical component. It's not specifically an x, y, but we can talk about horizontal and vertical to explain or to show or to express these two. So when we're graphing a complex number, we have the horizontal, kind of like the x, and then we have the vertical, kind of like the y. Remember, we're expanding what we know about complex numbers. And so here's the weird thing with complex numbers. If they ever ask us for the absolute value of a complex number, you would think, oh, just make it all positive. No, it doesn't work, because this isn't a normal integer. It's not a normal positive, negative, single real number. It has like real pieces, it has imaginary pieces. So actually, the absolute value of a complex number, down here when we find the absolute value of 5 minus 12i, it has nothing to do with making it all positive. It has everything to do with magnitude. Like vectors. Vectors have magnitudes, and complex numbers have magnitudes too. And actually, absolute value of numbers, like whenever I ask you, for instance, the absolute value of negative 5. Easy. It's a real number. That's it. What'd you guys all answer if I showed you that? Absolute value of negative 5? 5. Why? Way back when, in elementary school, you would have talked about, you would have talked about a number line. And you would have talked about how absolute value actually is asking the distance, how far a number is from 0. It's the magnitude of the number. It's the how muchness of the number, not the direction. It actually all comes back to vectors, which is really weird, just no one told you about a vector in elementary, or even in Algebra 1. The how muchness of negative 5, the absolute value of negative 5 is the distance it is from 0, which is just 5. And what's the distance that one is from 0? It's just 5. So whatever you're doing in absolute value, you're thinking about the how muchness of the number, regardless of the sign. So the how muchness of a complex number, it's the magnitude. And in vectors, didn't we learn magnitude is the magnitude? Perfect. So all we have to do down here is just, okay, magnitude. And some of you, maybe it would help to actually write the word magnitude, and some of you, it's better just to have the formula and say, okay, I'll just know what to do when I see the absolute value. But the idea is the absolute value of a complex number is its magnitude. I can do this math pretty quickly. I think most of you could too. Anybody notice the 5, 12, 13 triangle? Square root of 169 when we put it all together is 13. The absolute value of, which is really weird, the absolute value of a complex number is a real number. Huh. There's a lot of deep stuff that's in this section that we could go deeper on, we just don't have time. But did you guys notice there was another part to the directions? Plot the complex number. Okay, we didn't do that, which is why I left a little blank up here. But some of you could just do it off to the side. So plot, guys, what quadrant would 5 minus 12i be in? 5 is horizontal. So are we going right or left if it's a positive 5?
Right.
So we're going to go right 5, and then this is the vertical component, up or down? Okay. So if we go 5, and if we go negative 12, well, I guess I would even move this up a bit, huh? But if we go 5 and negative 12, we would be in the fourth quadrant. 5-ish, negative 12-ish. Sound good? Now, here's a question. It's not even actually on this page. But what if they were to ask me, hold on, we know vectors, despicable me from the very beginning. Vectors have magnitudes and
Direction.
Guess what? So do complex numbers. So what if they're asking me about not just the magnitude, not just the absolute value, but what if they were to ask me about the direction? I know they're not in that. But what if they were? Huh? Well, but the problem is complex numbers don't have an arrow per se. So maybe direction is more than just an arrow. Wait, yeah. How do we find direction with vectors? We weren't putting the arrows. I mean, we always put the arrows, but... No, not something over magnitude. There are formulas like that.
Would you use the projection formula?
Projection involves it. You guys are thinking too hard. Magnitude was the square root of a squared plus b squared. Direction was theta equals tangent inverse of b over a. All I mean is theta. All I mean is angle. Okay? So, yeah, you could have just done define theta, define the direction, tangent inverse of, wait, who would our b and a be for this guy? B would be negative 12 and a would be 5. Why? Horizontal comes first, vertical comes second. Wait, in vectors, which one came first? Horizontal, which one came second? Vertical. So complex numbers are super similar to vectors, but instead of side carets and commas, instead of I vectors and J vectors, we have real and we have imaginary. But we can use our same formulas, just they have a little bit different meaning, even though it's still magnitude, and it would still be direction. Now, hold on. Can we talk about this real quick? If you do tangent inverse of negative 12 over 5, I have some calculators out. Be in degree mode just to make it simple. When they find a negative number, which they are about to do you remember in vectors what we did whenever we saw a negative angle? Did the book use negative angles for their answers? No. So hold on. They're finding a negative angle. And what angle?
67.38.
Good, negative 67.38. The problem is that's what your calculator says. And on like a test, if you were looking at direction, really careful. We have two options, either adding 180 and getting to the second quadrant, or adding 360 and being in the fourth. What do you think I want for this? I need to be back to the fourth. So even though your calculator would say, I'm going to put a theta with a colon like we did in the notes. You use tangent inverse, but no negatives, positives. So we're going to add 360. Sorry, I heard you guys do it, but then I didn't know what the number was.
292.62.
So if they were to ask it, we have our direction and we have our magnitude. The formulas didn't change, just what they were used for changed. Well, let's come over here to complex numbers in trig form. So hold on. If I'm talking about magnitudes and directions over here, would it just be like vectors and like find the magnitude, find the direction? Well, maybe. They might say find the absolute value. All you have to do is find the magnitude and you're done. But the weird thing is with complex numbers, they don't just say like the word magnitude, the word direction, and say da-da, like they do in Despicable Me or like they did with vectors. They said, give us components. No, never mind. Give us magnitude and direction. We'll give you magnitude and direction. Go back and forth. It's like that game where you shuffle around a P. But anyway, coming back. You guys haven't seen that one? The one where you like have like a P underneath like cups and you find it? No.
Oh, I thought you meant like actual P.
Well, that's like the old, but now like they use like little balls or like a PEA, like the green vegetable that most of you probably don't like. Not my favorite. I green bean sugar. Okay, coming back. Well, Brussels sprouts. Nicely roasted with a salt and pepper. Anyway, coming back. Your taste develops usually when you get older. So, coming back. Yeah, that's the hard part. No, it's broccoli. Yeah, I totally opened the windows. Otherwise, broccoli's the same way, but I love it with like cheese and stuff like that. Huh?
The five minute like Dunkin' butter. Brussels sprouts.
I have you all roasted and nice and squishy on the inside and have like the leaves all crunchy on the outside. Coming back. But when they're boiled, ugh.
Oh yeah, no, never gonna boil.
Okay. Complex numbers in trig form. All veggies boiled. I don't know. Potatoes? Those aren't veggies though. Complex numbers in trig form. Here's the idea. I know. Too much fun, guys. There's a whole form for magnitude and direction. There's a whole form to show the magnitude and direction for complex numbers. It's weird, but there's a whole form. For vectors, there's not. It's like, what's the magnitude? What's the direction? Done. For complex numbers, they're like, no. There's a way to write the complex number to show the magnitude and the direction. So here's the dealio. Old school. Good. A plus BI. It is a thing. However, new school says take the A plus BI and say, okay, hold on. What is the R, aka the absolute value, aka the magnitude? And what is the theta, aka tangent inverse? And then let's take the magnitude, let's take the direction, let's put it in a whole different form. I know it's weird, I know it's kind of awkward, but there is a proper notation for taking magnitude, taking direction, and writing the complex number with those pieces, with those components. And I don't like to use the word components, but it's kind of the same idea. So what we're going to do is actually, whenever you see the R and whenever you see the theta, we're going to say, hey, you know what? This is just using magnitude. It's just using the absolute value of the complex number. Theta, we're going to use tangent inverse. And why am I saying use? Because we might have to check the picture, do we need to add 180? Do we need to add 360? Check the picture. Do we need to add 180? Do we need to add 360? Let's see if maybe one of these down here can kind of help us out as far as what to do when. Most of you guys probably don't care if these problems actually line up with ones in the book, right?
Yeah.
To that end, can I change this a little bit so we see something different than a fourth quadrant angle that we add 360 to? Can you guys change this example with me really quickly to be, instead of 1 minus root 3i, can you make it negative 1 plus? Let's change it real quick. Let's change the example really quick. All right, magnitude, no big deal. Take the horizontal, square it. Take the vertical, square it. You guys are allowed to have your calculator for the whole test. So what would you do? Throw the whole thing in, right? But I can do some mental math.
2.
3 plus 1 is 4, and the square root of 4 is 2. I agree. Okay, we have the magnitude. Done. Tangent inverse of b positive square root of 3 over a negative 1. Your calculator, wait a minute. Square root of 3 over 3, 1 square root of 3. This is a unit circle 1. Yeah. Square root of 3 is a pi over 3, except, okay, hold on. If you were, yes, it is negative. So it's not first quadrant. But what? People are going to be using their calculators, so they might not be thinking through the unit circle. So if they're using their calculators, the calculator is going to spit out for you negative 60 degrees. If I see a negative, am I in trouble?
Yes.
Slightly. Not big trouble. Slightly. I said check the pic, right? The pic of what? The picture of the complex number. Okay, where would he be? Negative 1, positive root 3. What quadrant?
Second. Third.
Good. Mm-hmm. Which one?
Second.
Horizontal, I go left. Vertical, I go up, right?
Yeah.
Something like this. But where's negative 60?
Opposite.
Something like that. Am I adding 360? I don't want the negative. Am I adding 360 to get all the way back to the fourth quadrant? No. Where do I actually want to get? To my guy. My guy's up here. So how do I get there?
180.
Add 180. Now, could some of you guys in your reference sheet right now make a note? Yeah. When do you add 180? When your guy is on the opposite quadrant from what your calculator says. When do you add 180? When your guy is in the opposite quadrant from where your guy is. That's an example right down here. When do you add 360?
Same line.
Yeah. When you have a negative angle in the right place that you need the positive. So for your reference page, tangent inverse of b over a is the answer unless you have a negative angle. We don't put negatives in straight form. We don't put negatives for vectors. When you have a negative angle in the right quadrant, we have to add 360. When do you add 180? When you have a negative angle or any angle in the wrong quadrant, in the opposite quadrant, and you have to get to the other place. So remember, your calculators are only so good as they're programming, and it's okay. It's totally valid that your calculators do this because calculators are only meant to tell us the answers to questions with one answer. You wouldn't ask your calculator, what am I supposed to have for lunch today? It's not like an 8-ball that maybe sometimes can pretend to give you the answer. Spinach. Popeye, it makes you strong. Anyway, but your calculator, it can only give you the answers to questions with one answer. Anyway, long story short, calculator will spit something out and you have to check the picture and see. Okay? Wait a minute, hold on. So we have our 120 degrees and we have our 2. We're done, right? Vectors just say, haha, magnitude, direction, done.
No,
Complex numbers say, no, I have a nice special form. It's okay. You have this written down in your reference page. All we have to do is say, okay, fine, you want the trig form. I'll write you the trig form. V equals what?
2.
R. Good, 2. Times cosine of
120.
120 plus I sine of
120.
120. Now, do any of you guys realize that we could actually plug this into our calculator and say, who is the cosine of 120 times 2?
Yeah.
Who is the sine of 120 times 2? Guess what that would get us?
That one.
Where we just came from. There are two different ways of writing it. This way says, hey look, magnitude, direction. I can go to 120, I can go out 2. Yay! This one says, oh, go left 1 and up root 3. Yay! Both of them get you to the same place. If they get you there different. So then when you come down to this one, and it says, write the standard form of a complex number. Well, yeah, just put it in your calculator. Some of you guys, oh my goodness, are already doing that. Because standard form says, I don't care about what you turn and what you go out. I want to know how much left and how much up. And how do you do that? Just plug and chug. Distribute your 5. Get the standard form. I just want that a plus bi. And I can do that just by plugging and chugging. And if you go in your calculator, well, if you did unit circle, because this is a 45 in the second quadrant, you get negative root 2 over 2 plus 5 times sine would be a positive root 2 over 2. But some of you are doing it in your calculator, and you're totally right. You're not wrong. I told you you're allowed to use it, right? When you plug this in, 5 cosine 135 degree mode, 5 sine 135. Does anybody have decimals for me?
Yeah, wait, okay, so for this, would you plug it in degree mode or radian? Degree? Oh, yeah.
Does that make sense?
Yeah.
Yeah.
So it's negative 3.54 plus 3.54i.
No, it's not I. Sorry, it's not 0. Matthew's over here saying 0. No, because remember, you go negative, the real, positive, like you have an actual location. Because this is an I, this is imaginary, and this is a real. We never combine those two because they're not like terms. Does that make sense? So go combining. Joe. Never mind. Has the math been hard so far?
No.
Well, really, the formulas are very similar, but is it used in new ways?
Yeah.
Are they used in new ways? Yeah. So let's go ahead and see, okay, well, how much harder does it get? Because you're like, wait a minute, we're supposed to be done. We're supposed to be doing the short, sweet version. So far, what have we seen? Complex numbers, we saw them a while ago, have another way of being written where basically you put in the magnitude of the complex number and the direction, kind of vectory math that we've already done. Oh, and by the way, the magnitude can also be called absolute value. So if it helps, you guys could put an R over here. Doesn't want to put it on. There are a couple different ways magnitude can be asked for. But let's see what else there is. I see that hand. Give me 1 second so people can see the next page. Because this is basically where we're ending. Jason.
Okay, so you were mentioning something at the beginning of the section about, like, part of this being in radians. Like, what part is that? Is it what we're about to do?
Yeah.
Okay.
And not so much because the end of the section will always be in radians. It's more like you just have to be aware, because check it. What were the angles over here?
Degrees.
What did I let you get the angles in?
Degrees. These are in radians. Gotcha.
So just because it's not vectors anymore, the angles can show up different ways. You just have to be ready. So it's kind of like section 6.5, you have to be on your toes as far as what mode you need to be in. Is that cool? Mm-hmm. Okay. Just to be ready. Just to be ready. But on the test, if it was like a multiple choice, and you tried plugging in what you knew, and it somehow used trig, complex numbers, like you should be able to see, oh, it's not matching up. Oh, I bet I need to be in the other mode. So hopefully that's something that can just be more of like a, you're solving the way you know how. It just doesn't quite match up. Yeah, I can zoom in. What I wanted you to see on the second page, just real quick from the first page or the page before, do you see now that we've learned trig form, everything is like trig form now?
Yeah.
Okay. That's what I wanted you to see. So now we're playing with complex numbers in trig form. Because complex numbers, way back in the complex number section, I don't even remember what it was, to be honest. But complex numbers in the complex number section, if it's an a plus bi form, it's so easy to add, it's so easy to subtract. Multiplying and dividing actually got kind of hard. We had to do some conjugates and I squareds and all kinds of stuff like that. So multiplying and dividing did get kind of hard. So we're just showing with complex numbers, if you have trig form, magnitudes, and directions of both, there actually are some pretty nice formulas. Once again, reference page, okay? There are some pretty nice formulas as far as how to quickly, easily, with r's and betas, multiply and divide complex numbers. how to multiply and divide complex numbers. And if you guys notice, the r's always kind of combine in one way, and the thetas always kind of combine in a different way. The r's kind of combine in one way, and the thetas kind of combine in a different way. I'm updating your homework really quickly. I've decided this will be our last page for section 6.5. So I'm taking out something called the de Moivre's theorem. Sounds like fun, but we're just going to go ahead and stop here. De Moivre says how to raise to a power. I'm going to go ahead and put lines over these pages in your notes so that you know you don't have to worry about these pages. Okay. This is homework 41 here. Let me see if you guys can still see it. If I zoom out just a little bit, are we still okay?
Yeah.
Okay. So long story short, I have two different complex numbers. I want to multiply them together. I have two complex numbers. I want to multiply them together, or I want to divide them. We could get them in standard form, both of them in standard form by using our calculator. And then we could do something like, hey, let's go ahead and multiply one of the a plus bi's times another of the a plus bi's. And then we can remember that when we're multiplying, we'd have to do some foiling, and when we're doing foiling, we're going to get some I squareds, and when we get I squareds, we have to make it negative 1s. And we could do this, and then put it back into trig form. Or we could just write down our formulas and use them, because our formulas say, if you have two different complex numbers that need to be multiplied, we can call this one Z1, we can call this one Z2. If we have two different complex numbers being multiplied, basically, without having to do all the math, everything that would happen if we would FOIL everything out would actually come back to cosine A plus cosine B, be a co minus a sine. And this is going to be a cosine plus a sine cosine. But the nice thing is we don't have to do all that work. Instead, all we have to do is say, oh, this is going to work. Yep. Every time? Yep. Then we'll do it. What are we going to do? Who's your R1 and your R2 of these two guys?
2 and 6.
Yeah.
2, 6.
So you just say, oh, hey, if you were multiplying these two, 2 times 6 would be 12. Yep, you're totally right. Oh, man, you would have to FOIL all of this stuff. Yeah, you would, and what ends up happening? You actually end up getting all the way back to these little formulas from last chapter. So the cool thing is, yeah, exactly, Joe. The cool thing is we can do the shortcut. We can say, okay, cool. So you tell me every single time I can add these two together? And the answer is yes, when you're multiplying. And then every single time, I can do that for sine also? Yes.
Is that the one?
Yeah. Joe basically what's saving us is all the foiling and then all the cosine sine and making it match backwards. So it's legal to do the shortcut, and the shortcut is the rule you guys just wrote down. So all we have to do to finish this off is maybe off to the side be like, wait a minute, how do I add fourths and twelfths? Anybody thinking common denominator times 3? Right? So 3 pi over 12 plus 1 pi over 12 is 4 pi over 12, which is?
Pi over 3.
Pi over 3. Well, let's see. All we need to know basically is do they want the trig form or do they want the standard form? Because trig form, I'm done. Oh, I didn't put the 12, I'm sorry. What do they want, standard or trig?
Trig.
Okay, we're done. What if they want a standard?
Plug
Plug it in your calculator. Yeah. You'd be like, fine, I'll get you the A, I'll get you the BI. But they said trig form, cool. Well then, how does the dividing formula work? Well guys, if we were dividing, wouldn't we?
Minus, just change to minus.
Well, but the 5 is over the 4, right?
5 over 4.
R1 is over R2. 5 is over 4. But then, if we were to multiply by the conjugate, and do all sorts of, we would eventually, it'd take a long time, end up at just what Joe just said. Did you guys write down the division formula? It just says minus, right? Just subtract the angles. So what's the final result?
5 over 4 times.
Cosine of what? 2.2? Anybody like line it up and subtract them? Cosine of 2.2 minus I sine of 2.2.
Is it plus? Or I sine?
What's your?
Is it plus for the I sign outside?
I just randomly made it a minus because I said minus when I was subtracting. Man, it's all okay. How bad are those formulas?
Not bad.
Not bad.
Just
Not horrible. Okay, here's the dilemma, kiddos. We have 3 minutes left of class, and we haven't been able to look at the evens for section 6.4. Why is that bad? Because you don't know if you got them right or wrong. Now, do the odds, or in the odds, do you know whether or not you got them right or wrong? Yeah, but the evens you don't. So here's what I'm about to do. Ready? I'm recording this whole lecture, yeah? Okay. And as I'm recording this whole lecture, where is this accessible as far as for you guys online? YouTube. I mean, you could search Miss Dueck HCS. That's one way. Or on Google Classroom, because you all go there to find your homework assignments anyway, right? Isn't there a way to get to it from Google Classroom? Yeah, exactly. So if I pull up Google Classroom, number 1, there is an adjustment to tonight's homework. So if you want, it is online. But you can also get your phones out to take a quick picture of the new updated homework assignment for tonight. The new updated homework assignment for tonight is this one right here, if I can get it up. I've cut out the last 2 problems because the last 2 problems are from these pages of the notes I decided that we're just not going to do this year. Okay? So, the updated homework assignment, if you want it. There it is. But it's also in Google Classroom. It's live. It's updated. We're good. However, in Google Classroom, you can also get to my YouTube channel, true? If you go in the second tab in your phone when you have it up, not the first tab, but the second tab, I think for you guys it's on the bottom of your phone screen. Class resources, you can get to my YouTube channel real fast and get to the video from today. Okay? Why am I telling you that? Because right now, I have section 6.4 on the video ready to grade 2 and 4 and 12 and 82. Could you compare that to your homework tonight and see how you did?
Yeah.
However, guess what else I'm going to? Wait a minute, what? I was going to show you 6.5 because I was going to let you guys check the evens. What do you notice? They're all odds. Now, wait a minute. You don't have 71, 79, right? I cut them out.
Yeah.
But they're all odds. What does that mean? Tomorrow, you should be able to, and some of you can grade your homework spirals right now. Technically, we still have another minute. Technically, tomorrow, you should be able to come in with homework 6.4, 6.5, knowing exactly what you're stuck on. Does that make sense? Mm-hmm. Evens, odds, you know what the answers are from either count chat or from right here the video, or taking a quick picture of it right now with your phone, not having to worry about YouTube. Totally fine. Do it quick. That way, at the beginning of class tomorrow, we can go over the questions you guys are stuck on, 6.4, 6.5. I can give you really specific hints about the test, which I've been doing all chapter. And you've been highlighting things in your notes to make sure your reference pages are good. And then test on Wednesday. Now wait, are we going to start the review tomorrow? Yes. What would be awesome for you to already have made with maybe a little bit of extra space just in case something comes up again? Because if you have your reference page ready for tomorrow, can't you do or use it on the whole review? And what are you doing? Practicing using it with problems to make sure everything is on it. Now pause. Reference pages can only have what sections? Vectors to the end.
Yeah.
Okay. What do you have to memorize? 6.1, 6.2 formulas. Are we good?
Yeah.
Get out of here, cool. I'll see you later. Good job. Good job. Good job. It's a good test. It's a good test on Wednesday. Yeah. Leaving at 1:30. It's like 11. Does that make sense? Okay. Yeah. I just don't want you to be like, orthogonal, what's that? But no joke, that's
I
fine.
knew that's perpendicular, but I wrote perpendicular.
It's totally fine. I understand. Because it was the same idea, meaning, right?
Bye.
Bye.